Merhaba arkadaşlar, günaydın. Birazdan başlayacağız. So before we start, if you have any question, please ask. All right, so last time we talked about this impulse function and Laplace transform of impulse function. And we did one example with that. Now let's continue with convolution. Convolution is used to compute some Laplace transforms of complicated functions. Okay, so let's talk about this. This is 6.6 in the book. Convolution. So let's define first what is convolution is. Well, we take two functions. So here, the convolution of two functions f, g is defined by basically f. We will denote this by star, f star g, okay, f star g. Here just denotes the convolution of f with g, and it is given by, it's a function again, okay, it's a function again, and it is given by this formula from 0 to t, f of t minus, let's say, w, okay, g of w dw, okay. So this formula defines the convolution of f with g. Well, we have some results here. The important one is this one, the theorem here. This is why we're interested in convolution in this course. The Laplace transform of f convolution g is basically the Laplace transform of f times Laplace transform of g, okay? So you multiply Laplace transforms of both to compute the Laplace transform of the convolution. This is important when we find the inverse Laplace of f and g, okay? And effect here, so this, we should keep this in mind, an important formula here, and effect here, you can easily check that f convolution g is same as g convolution f, okay? So you can switch the order and the convolution, and nothing will change. Let's see how we use this theorem to compute the inverse Laplace. An example here. So let's find the inverse Laplacian of a over s square times s square plus a square. Well, there are different ways you can do this. For instance, you can do the partial fraction decomposition and find the inverse Laplace of each factor in the partial fraction decomposition. But the easier way here is, since we know that the Laplacian of sine at is what? It's a over s square plus a square. So it is this one, right? And we multiply this with 1 over s square. So what is the Laplacian of the other one here? 1 over s square. Okay, so this is like 1 over s square. So the Laplacian of t, right, is 1 over s square. We know this, right? Well, basically we have here the Laplacian of t times Laplacian of sine at is equal to a over s square plus s square times s square plus a square, right? So this tells you basically by the theorem, this one here, the Laplacian of t convolution sine at, okay, it's what? It's the Laplacian of t times Laplacian of, this is what the theorem says, right? Sine at, but this is what we just found here. It's a over s square times s square plus a square, right? But this implies basically that the inverse of the Laplacian of this here, inverse Laplace transform of this function is equal to t convolution sine at, okay? And the nice thing here is we get this, right? We know how to compute the convolution. The convolution is by the definition. This is like in the convolution, this is like f, okay? And this is like g, okay? So the convolution formula is the following. It's 0 to t f of, remember here, where is it? T minus w times g of w, right? dw. Well, it's basically, maybe let's write it here. Now, 0 to t, f of t minus w, f of t is t, so t minus w times g of w is sine a w, okay, dw. And we will compute this integral. Well, we will do this by integration by part. So you can say this is here u, we will get rid of this, okay? We will kill this by saying q, and this is dv, let's say. So integration by part will give you u times v, which is t minus maybe down here. Okay. Or maybe let's write here. Du is here minus dw. Okay, let me say like this. Yeah. Okay, and v is what? V is the integral here with respect to w, so it is minus cosine a w over A. Okay. Yeah. All right. So it becomes basically u times v, which is t minus w times v minus cosine a w over a. Well, like this minus cosine. Okay. Here, w is from 0 to w is from 0 to t. Okay. Minus integral v times du minus cosine a w over a times du is minus dv. Okay. And again, here w is from 0 to t. All right, let's compute this. When you plug w is equal to t, this one will vanish, right? When w is equal to t, it's going to be 0. When w is equal to 0, it's going to be, so minus, when w is equal to 0, it's going to be t times minus cosine 0. Minus cosine 0 is minus 1 over a, okay? All right. This is the first part. Now we move to the integral here. Plus, minus, minus, plus, but there is another minus here. Okay, so we get cosine. Okay, so minus 1 over a cosine aw. The integral of cosine aw is sine aw over a. Okay, and here w is from 0 to t. Well, let's see what we get. It's t over a, okay, minus 1 over a square.
Hocam, buradaki t over a başında artı oldu ya.
Evet.
T'den W'ye çıkardık. T'den W'ye çıkardık. Tamam, anladım hocam. Teşekkürler.
Tamam, bir tane daha soru var. Ona da bakalım. Minus sign at the beginning. Why do we have minus sign at the beginning? Because you plug t first, okay, and then you get 0. Minus, then you plug 0 here, okay. When you plug w is equal to 0, it's going to be t over, okay, and minus 1 here. Make sense? Okay.
I don't want to lie, I didn't get it actually.
All right, so you first plug t, right? You first plug t. When you plug t, you will get 0. right?
Mm-hmm.
And then you plug 0. When you plug w is equal to 0, let's see what we minus, right? Minus, then you
Okay, okay. Yes, yes.
plug 0 for w, okay?
Yeah, yes, thank you. Got it.
Right. It's like this f of w is equal to 0 to t. This is f of t minus f of 0, okay? Like this. Okay, well. All right, so let's continue this. So what we get is okay, so it's going to be 1 over a square sine at a sine 0 is 0, so you will get nothing from 0 part sine at. Yeah, that's it. So we find out that the inverse Laplace of this is equal to this function. Okay. Any question with this example? Var mı soru arkadaşlar? Yani convolution. So what makes the convolution here is convolution returns, well, Laplace transform returns convolution into the product. Okay, so this is how we use convolution. Or inverse Laplace returns product into convolution. Okay, so if you have the product of two Laplace transforms, you can find the inverse Laplace transform using convolution, basically. All right. Let's do one more example with this. Solve the initial value problem, IVP, y double prime plus 4 times y is equal to g of t. Well, here the initial values are y0 is equal to 3, and the derivative at 0 is equal to -1. Okay. We don't know what g is here. Okay, g is not given. We know it's a function, but that's it. So we will find the solution in terms of g here. Well, since we don't know g here, we cannot use, for instance, undeterminate coefficient, or we cannot use variation of parameters, because in those we need g, right? We need to know g and write some formulas for this. But we can try with Laplace transform here. So let's do it. So when you apply Laplace transform, we will get the following, right? The Laplace transform of y double prime plus 4 times the Laplace transform of y is equal to the Laplace transform of g t. Well, let's say the Laplace transform of y is maybe here. Say Laplace transform of y is y, capital Y of s, okay? Let's use this notation as usual. Well, remember, this gives you the following: s squared times ys minus s times y of 0, which is 3, okay? Or maybe let's write it a long way. Y of 0 okay, minus y prime 0, okay. This is the first part, this part here. Now we continue with this one. Plus 4 times, this is nothing but ys, is equal to, let's call this here g of s. It's going to be a function of s after you apply the Laplace transform. So let's call it g, okay, capital G. Well, that was 3, and this was -1. So we get basically in ys parentheses s square minus 3 s, okay, s square only, sorry, s square plus 4, right, on here, s square plus 4, and we will have minus 3s plus 1 is equal to g of s. And this implies, right, y of s is equal to g of s over s square plus 4 plus 3s minus 1 over s square plus 4. Now let's apply the inverse Laplace transform. When we apply inverse Laplace transform, we will get y of t is equal to the inverse Laplace of g of s over s squared plus 4 plus the inverse transform of this. Well, you can separate this, split this into 2. So it's going to be 3 times the inverse Laplace of s over s squared plus 4. This is one thing. And the other one is minus the inverse Laplace of 1 over s squared plus 4. Okay. The last two are simple. The first one, we need the convolution. So it's equal to, again, by the theorem about the convolution, remember, it's nothing but g of t convolution, the inverse of 1 over s squared plus 4. Okay, this. Next, 3 times the inverse Laplace of this, it's like cosine, right? Well, remember cosine. Here, this is 2 square, okay? 2 square, so it's going to be cosine 2t. Okay? When you have s here, it's cosine. When you have a number above, you have sine, okay? Minus, now you have a number here, that means it's the Laplace transform of sine function, sine 2t, but there is no 2 here, it's 1, so you will divide by 2. Sine 2t, okay, that's it. We are almost done here. Well, this is what? The inverse Laplace of this is basically, again, sine, we just compute here, it's 1 over 2 sine 2t. So we're almost done. You can leave it like this if you want, but if you write the explicit formula for the convolution, it's going to be better. So the explicit formula is 0 to t g of t minus w sine 2t over 2 d, sine 2 w dw. Okay, so this part is basically the convolution part. Now let's continue. Plus 3 cosine 2t, okay, minus sine 2t over 2. That's it. Any question with this example? Var mı soru arkadaşlar?
Don't we need to open it? Don't we need to proceed?
We cannot because we don't know what G is. Okay,
Okay, got it. Thanks.
we don't know what G is, so we cannot go further than this. All right, we're done with Laplace transform with all these details. Now we will move to a new chapter. This is chapter 10. So we'll talk about now totally different thing. It's partial differential equation. Okay, here we will talk about partial differential equations, PDE. That means we will have two variables, x and y, and we will differentiate with respect to x or y, and we will get a differential equation with respect to partial derivatives. Okay. Before we do that, we will talk about first again sort of an ordinary differential equation again. This is partial differential equations. And we need also Fourier series. We'll talk about this. First, we'll talk about two-point boundary value problem. This part is not partial differential equation. We will come to partial differential equations later. Okay, so this is still an ODE problem. Ordinary differential equation, okay? And this is PDE. Well, let me recall the existence and uniqueness theorem for the initial value problem. We call this the IVP, initial value problem, given by y double prime plus p of x, y prime plus q of x, y is equal to g of x, let's say, and the initial conditions are y x0 is equal to some number y0, let's say, and the derivative at x0 is equal to, let's say, y1. So it's an initial value problem, second order differential equation, right? Linear. And we know that this has a unique solution. Near x0 if p, q, r are all continuous, okay? P, q, r, p, q, g, sorry, are all continuous near x0. 0. Okay. We did this at the beginning of this course. Now, the 2-point boundary value problems are basically you replace x0 by 2 points. Okay, instead of x0 in the initial conditions, we replace x0 by 2 points. So replace x0 by 2 points in the initial values, initial conditions. So what I'm saying is the initial conditions will be y, let's say alpha, okay? Instead of x0, we have alpha now. Y alpha is equal to y0. And the other point is beta. Y beta is equal to y1 for some alpha different from beta. And they are both real numbers, okay? So you replace 1 point by 2 points, and it becomes a 2-point boundary value problem. Let us define this now. Definition. A differential equation y double prime plus px y prime plus qx y is equal to g of x, and the initial values are y alpha is equal to y0, y beta is equal to y1. This is called a 2-point boundary value problem. 2-point boundary value problem. Okay. So what is the difference between the initial value problem at the beginning of this course? Well, now we have the initial values are at 2 points, and the most important thing is in this case we do not have existence uniqueness theorem. Okay, so let's write this as a remark. Existence uniqueness theorem may fail for 2-point boundary value problems. Okay, that means in some cases, even if you have continuous coefficients p, q, g are continuous, we may have more than one solution, infinitely many solutions, or we may have no solutions. Okay, so existence may fail or uniqueness may fail. Sometimes it works, but it doesn't guarantee the unique solution. Okay, in this case, let me give an example, and we will get a better idea what happens in this case. So let us solve. By the way, these are called boundary value problem. For short, we will write BVP. Okay. Okay. So solve the boundary value problem. Y double prime plus 2y is equal to 0. Okay. Y0 is equal to 1, and y pi is equal to 0. All right. So let us try to solve this. Yeah, it's an easy second order differential equation. It's homogeneous, coefficients are constant. So we write the characteristic equation to solve it. The characteristic equation is lambda r squared, or lambda, okay, we use r squared plus 2 is equal to 0, which implies r is equal to plus minus 2i. So we have complex solution, and we have for each complex solution we have two real solutions. We can use one of those. Let's use 2i. It's y of t is e to the 2i. Well, sorry, this is root 2, right? Not 2. Root 2i. Root 2i of I times t is a solution which is cosine root 2t plus I times sine root 2t is a complex solution. Without the initial values, okay? Without the initial values. We didn't check the initial values yet. So the general solution is well, you take the real part and imaginary part, right? This one, that one. So it's gonna be y of t is c1 times cosine root 2 times t plus c2 times sine root 2 t. What is c1 and c2? We can find c1 and c2. Maybe I should say here without the initial values, okay? Without initial values. Now we consider the initial values to find c1 and c2. What is the first initial value is y0 is equal to 1. So y0 is equal to 1 means what? You plug 0 for t, cosine 0 is 1, sine 0 is 0, so this is c1. So we get that c1 is equal to 1. Y pi is equal to 0. What is y pi? When you plug pi in cosine root 2 pi, let's write it, okay, let's write it like this. Cosine c1 times cosine root 2 pi, okay, plus c2 times sine of root 2 pi, and it's equal to 0. Well, we already have c1. c1 was 1, right? It's 1 from here. So this tells you basically c2 is what? c2 is minus cosine root 2 pi over sine root 2 pi, which is the cotangent minus cotangent root 2 times pi. Okay, so we find C1 and C2. Now we can write the general solution. So this implies basically y of t is equal to C1 was 1. So cosine root 2 t plus C2 is, okay, minus here. C2 is minus cotangent root 2 pi, whatever it is, okay, times sine root 2t. So this is the solution of boundary value problem, okay? So we get a unique solution in this case. In this case, unique solution to boundary value problem, okay? Any question here?
Hocam buradaki pi radyan değil mi? Mesela bunu 180 dereceye çevirip
Evet, bu
180 radyan, tamam.
Radyan. All right, let's do another example. Well, let's remember this example again here. It's y double prime plus 2y is equal to 0. Initial values are this, and we get a unique solution in this case. If we change this a little bit, let's see what happens. Now the boundary value problem is y double prime plus y is equal to 0, y0 is equal to 1, y pi is equal to 0, okay? So it looks like the previous one, but now we have, instead of 2y, we have y in the equation. All right, let's solve it. Well, again, the characteristic equation is r squared plus 1 is equal to 0, which implies r is equal to plus minus I, which implies we have the complex solution is e to the, let's take one of those, it, okay, is a complex solution. So the real part is cosine t and imaginary part is sine t. So we write basically general solution. Let's call it y1 is a complex solution, and general solution is yt, which is c1 cosine t plus c2 sine t. With the initial values, let's try to find c1 and c2. 1 is equal to y0. Y0 is what? If you plug 0, sine is 0, cosine is 1, so we get c1. So c1 is equal to 1. But if you plug pi, you will get 0, right? Y pi. Again, now cosine pi is what? Minus 1. So minus c1. Sine pi is 0. So we get that. From this, c1 is equal to 0. But in the first equation, c1 was 1. Now we have c1 is equal to 0. That means there is no solution because there is no such c1, right? c1 cannot be 0 and 1 at the same time. So let's call this star, okay? Star has no solution. So you see here the coefficients are here 1, 1, and 0, which are constant function continues everywhere. So the existence uniqueness theorem, the conditions of existence uniqueness theorems are satisfied, but it doesn't guarantee the existence of the solution. As we said at the beginning here, existence uniqueness theorem may fail when we have two boundary value problems, okay? And here we have two boundary value problem and we don't have any solution. So this theorem doesn't guarantee the existence of the solution in this case. Any question? Var mı soru arkadaşlar?
Sorry, I didn't get one thing. So in y in parentheses p, we
Yeah.
put p inside this sinus and cosinus t.
Yeah.
And sorry. I was thinking about p divided by 2. Yeah, it's actually 0. Yeah.
Yeah.
Thanks.
All right. Any other question, comment? Evet.
What's the difference between initial value and boundary value?
Our initial value, we have one initial point. Let's maybe call here. You see there is only one point x0, okay? x0. This is initial value problem. Boundary value problem, we have more than 1 points. Here, for instance, we have 2 points, alpha and beta, okay?
Okay, thank you.
2 different points, then it's called boundary value problem. All right, any other question? So that part is actually not the partial differential equation part, because again, we have first, we have derivative with respect to one variable, y prime, y double prime, the variable is x, so it's an ordinary differential equation. Now we will move to partial differential equations, and we'll talk about this. But before that, we need to talk about Fourier series. So let's give a break here for 10 minutes, and we will continue with Fourier series and use of it in PDE in the next hour.
Hocam ben bir şey sorabilir miyim geçmeden araya? Şimdi burada mesela son örnekte şey yoktu, çözüm yoktu ve
Evet.
yani tekliği, çokluğu falan filan hakkında konuşamadık.
Evet.
İlk çözümde exist and unique'ti.
Evet.
Mesela şey olabilir mi? Exist olsun ama çok.
Güzel soru, olabilir. Öyle de örnek var. Yapmadım ama var. Yani kitapta muhtemelen var. Hatta bulursam yazarım ama o da olabilir. Yani birden çok sonsuz tane çözüm de olabilir.
Anladım. Tamam, teşekkürler hocam. Kitapta buluruz. Sağ olun.
Okay, let's give a break here. Okay, welcome back. Here's an exercise which shows there are infinitely many solutions. It was a question by Kubra. Okay, any other question, comment? All right. So let's continue with Fourier series. This is 10.2 and 3 in the book. Fourier series. Well, let's define first what's the periodic function. Here is the definition. A function is called periodic, as you can guess. It's defined by the following: a function f is called periodic with a period t if f of x plus t is equal to f of x for all x in the domain of f. Okay. So when you basically shift your function by t units, you will get the same value. Okay. Well, let's give some examples, the important ones. Well, you can guess it's going to be something with sine and cosine, right? Sine and cosine are the usual periodic functions because it repeats itself infinitely many times, right? Sine n times pi x over L, let's say. Okay, here n is a natural number and L is any real number, let's say. And cosine n pi x over L, these are periodic with period t is equal to 2L. You can check this easily. Let's check sine function, for instance. What is sine n pi? Instead of x, we will write x plus 2L, okay, over L. It's nothing but sine n pi x over L plus you multiply this with 2L over L, so it's going to be 2n pi, okay? And well, of course, 2n pi will not change anything because sine is already periodic by 2 pi, so it is sine n pi x over L. Maybe I should say here n is here. N is a natural number, okay, like 0, 1, 2, 3, and so on. Okay, it's a natural number, and L is a real number, arbitrary real number. These functions are especially important. Later we will use it. Okay. here let's talk about this important theorem now. Which says basically a piecewise continuous function, which is periodic by 2L, can be written in a certain form, and this is called the Fourier series expansion. And the theorem is called Fourier convergence theorem. Fourier convergence theorem. Well, okay, there's one question. What happened to this this here 2 pi n 2m pi 2m pi will not change the value of the sign, right? And because sine is 2 pi periodic. Okay, that means if you add a number 2 pi to a number, the sign will not change, right? It's like sine pi is equal to, for instance, sine pi plus 2 pi. And it's sine pi plus 2 pi plus 2 pi. So if you add a multiple of 2 pi, it will not change the value of the sine function. And similar for cosine. Okay. All right, let's talk about this important theorem, Fourier convergence theorem, which says for a piecewise continuous, so suppose that we have f, which is piecewise continuous periodic function with period t is equal to 2L. Okay, so it has period 2L. L is a real number, positive real number. You can consider this a positive real number. Then f of x is equal to, let's take this down a little bit. A0 over 2. A0 is a number. Later we will find out those coefficients, A0, A1, and so on. Plus the sum an cosine n pi x over L. N is from 1 to infinity, plus the sum Bn sine n pi x over L. N is from 1 to infinity again. Okay, so this says basically for any periodic function you can write as a combination of sine and cosine functions. Okay, here the coefficients an and bn, we will determine this later. Right now it says you can write any periodic function as a combination of sine and cosine functions plus some constant. All right. And this here is called the Fourier series of f. Okay, here, this is called the Fourier series of f of x. I should say this equality holds when f is continuous at x, okay? Otherwise, we need to change a little bit. Maybe let's continue this. For equality holds for all x where f is continuous. Okay, so if f is continuous at a point, at this point we have this equality. Well, at the point of discontinuity, at the point of discontinuity, let's say x, okay? Let's say at this point x, f is not continuous, but it's right continuous and left continuous because it's a piecewise continuous function. It's like this. For instance, there's one, and so it's piecewise continuous. Each piece is continuous, so at least we have right limit, left limit, but at some point we may have discontinuity, we may have a jump. And at such a point, the similar formula holds, similar equation holds, but on the left-hand side, instead of f of x, we will have the following. Maybe let's say this star here, okay? So in star, replace f of x, the left-hand side here, we replace f of x by f of x minus plus f of x plus over 2. What is this? Well, basically, x minus and x plus, these are left limit and right limit at x, okay? Where fx minus is the left limit from left, okay, at x, and fx plus is the right limit at x, okay? So at the discontinuity points, for instance, let's say we have such a point like this, and at 1, okay, let's say this is 3, this is 2, okay? So instead of f of 1, we will use f of 1 plus f of 1 minus over 2, and this is nothing but right limit is 3, left limit is 2, so divide by 2, it is 5 over 2, okay? 5 over 2. F of 1 is 3, so we don't say f of 1 is equal to the Fourier series, but this, the mean, which is 5 over 2, is equal to the Fourier series at this point, okay? This is an example. Any question with this? So this formula is very important. You should keep this in mind, okay?
Sorry, what do we mean by A0?
A0 is a number. We will find out this later. It's a coefficient like A1, A2, and other ones like this, okay?
Mm-hmm.
Your answer starts with 1. So it's a number, and we will figure out what A0 is later, okay? Maybe I should say here AN and BN. These are some real numbers for all n bigger than or equal to 0, okay? All right, any other question? So let's find out this coefficients in terms of f. Before that, we need to introduce an inner product. So if you took linear algebra course, you should be familiar with this. But anyway, we will define here inner product. So our goal here, find an and bn in the Fourier series. So this is like Taylor series or power series, but instead of power functions, we have sine and cosine, and a and bn are the coefficients, right? Remember, in the case of power series, we have a n x to the n. Now, instead of x to the n, we have cosine x, sine x, okay? This is special for periodic functions, okay? All right, okay. Find an and bn in the Fourier series. Well, to do that, we need to introduce inner product. So let's take two periodic functions, that f, g, b, two piecewise continuous 2L periodic functions. And we define the inner product by the following formula: f comma g. This is the inner product of f with g. It's equal to the integral from minus L to L, f of x, g of x, dx. Okay, so this is the inner product. So inner product takes two functions and returns to a value. After you integrate, you will get a number, right? So it's like inner product here, f and g. It's a function which returns function to a real number, okay? So this, at the end, it's an element of real numbers, okay? Well, let's write some properties of this. Some properties. You can realize that when you change the order, nothing will change because you change the order in the integral. F times g or g times f doesn't make any difference. So f comma g is same as g inner product with f, same. For complex valued functions, these are different, but these are real valued functions, okay? So they are the same. We are not interested in complex valued functions for Fourier series, so this is true. You can change the order. Second, f1 plus f2 is a function, and you take the inner product this with g, it's nothing but the inner product of f1 with g plus the inner product of f2 with g. So basically you can distribute, you can split, sorry, inner product into two parts like this. And the last one, when you multiply a function by a constant, c is a constant here, and take the inner product with g, this is nothing but c times f inner product with g. Here, c is a constant, it's a real number, okay? So these properties are trivial ones and they are important for computations. Well, to find, remember our goal here, to find the Fourier coefficients. These are called Fourier coefficients. To find Fourier coefficients, we will need some special linear products. Let's talk about this. To find an, bn, we need the following result. It's a direct computation. One results, let's say one. The first one is when you take the inner product of sine n pi x over L with sine m pi x over L, okay? Here m and n, these are natural numbers. It's equal to 0 if m is different from n, okay? So if these two numbers here, m and n, are different, then the result is 0. You can do this yourself by using this integral, okay? Put this in integral and you can compute this integral easily, that it's going to be 0. Well, actually, if m is different from n, in the integral, we will have an odd function. And when you have an odd function, this integral will be 0, right? Minus L to L. If you integrate an odd function from minus L to L, you will get 0, right? We know this from calculus. Okay, so this part is easy. And if they are the same, then it's going to be equal to L. Now, this is not very trivial, but you can directly compute this. It's a direct computation. If m is equal to n, the result will be L. And in that case, you take the square of sine function and you use this formula. Remember this way. It's sine square x is equal to I guess minus cosine 2x plus 1 over 2, something like that, right? This was. So use this trigonometric identity to compute that integral, right? You can do it yourself and you will get that it's equal to L. The second one here is about cosine function, cosine n pi x over L and cosine m pi x over L. Well, now there are three cases. If again m is different from n, it's going to be 0. You can check this yourself. Well, if m is equal to n is not equal to 0, they are equal to each other but not 0. In that case, it is equal to L, like in the previous one. But we have one more thing. If they are both 0, then it's going to be 2L. Okay, if m is equal to n is equal to 0, then we will get 2L for this. Again, it's basic integration. You can check this yourself. And finally, cosine n pi x over L sine n pi x over L. Okay. Well, in that case, it's always 0. Regardless of m and n, it's always 0. Okay. Again, you can see this again from the formula. In the formula, you multiply this 2 and integrate from minus L to L. So when you multiply cosine with sine, you always get here, if at least one of them is non-zero, you will get m or n. You will get an odd function, and the result will be 0. If it's 0, you can compute it. If m or n is 0, you can compute the integral directly, and you will get that it's equal to 0. Okay. All right. Now let's find the coefficients. Do you have any questions so far?
Hocam birinci case'de L olabilmesi için n ve n'in eşit olduğu durumda aslında sıfırdan farklı da olacak. O da şartlardan birisi mi acaba?
Düşünelim.
Çünkü sanki sıfırın integralini mi o zaman alıyor gibi oluyoruz?
Evet. Doğru. Sıfırdan farklı olacak. Sıfır olursa çünkü sıfır olacak değil mi?
M ve n sıfır olursa sinüs sıfır.
Doğru. Doğru. Onu belki not edelim buraya. Tamam.
M, n eşit değildir.
Sıfırdan farklı. Sıfır durumu bizim için önemli değil. Onu belki söylemek lazım. Çünkü Fourier serisinde şurada sinüsle ilgili kısım n eşittir 1'den başlıyor.
Zaten sıfır diye bir condition'ımız olacak.
Evet, aynen öyle.
Sinüslü kısım. A sıfırla ilgili henüz bir şey demedik ama.
Demedik, evet. Onu
Hocam burada üçüncü case'de de yani m ve n ile ilgili herhangi bir condition belirtmedik.
evet, bu for all m and integer. Her doğal sayı için doğru, sıfır da olabilir. Zaten birisi mesela sinüs m sıfırsa sinüs sıfır oluyor. Sıfırla çarptığın zaman yine sıfır olacak falan.
Tamam, çok teşekkürler.
Peki, alright, let's now find the coefficients. So recall the Fourier series first. It was, where was it? Let's see, here, this one. So maybe let's copy this. Oops. Well, f of x was this, right? It's equal to a0 over 2 plus sum of an cosine n pi x over L n is from 1 to infinity, plus the sum bn sine n pi x over L, n is from 1 to infinity. Well, now let's to find here an, we will consider the inner product of f with cosine m pi x over L, and let's see what we get from this. Okay. Well, f of x is here it's given by, let's write explicit here, a0 over 2 plus a sum an cosine n pi x over L plus bn sine n pi x over L. Okay, this is f of x, comma, cosine m pi x over L, right? So we have this. Remember, we can distribute, we can split the inner product. So we have 3 inner products from coming from this one. Let's write each of them. The first one is, you use this one, a0 over 2, and this one. Okay, so we get basically a0 over 2, comma, cosine m pi x over L. This is the first inner product. Next one is coming from this one and this one here. Okay, so plus the inner product sum is an cosine n pi x over L, and the next one is cosine m pi x over L. Okay, the last one will come from this one. Okay, so plus the inner product bn cosine, sine, sorry, n pi x over L, comma, cosine m pi x over L. Well, let's see what we get. The first one here, a0 over 2 and cosine m pi x over L, okay, what is it? Well, if Okay, so this is gonna be 0 if m is different from 0. This one is equal to 0 if m is different from 0. The reason is if m is different from 0, well, it looks like this one in this case, okay? Cosine m pi xl, okay? And a0, how do you obtain a0? You can take a0 out, for instance, and this becomes like, if this is equal to 0, then you will get cosine 0 is equal to 1, okay? So it's like a0 over 2, 1, and cosine m pi x over l, like this, okay? And 1 and this is 0 if m is different from 0 from the second one, okay? Right, because if n is equal to 0 and m is different from n, which is m is different from 0, then you will get 0. Okay, good. So we use this one, number 2, to get that this is equal to 0 if m is different from 0. And next one, well, maybe let's do the last one. The last one is always 0. This is always, sorry, this is always 0 by 3, right? Because it's sine and cosine. Remember here, sine and cosine, this one gives you 0 in the inner product, always, okay? So it's always 0, all right? So what is left here? The only thing left here is this one. Okay, what is this? Well, we have cosine, cosine, right? And remember, when you have cosine, cosine, number 2 here says it is non-zero if m and n are the same, but not 0. Okay, so it's equal to L. So this is equal to, maybe, let's do this with this one. It's equal to L if m is equal to n is equal to not 0. So we assume that here, maybe at the beginning, first we assume that m is not 0. Okay, if m is not 0 and m and n are non-zero, it's equal to L in the case of m is equal to n. So what you get, let's summarize here what we get from here. From the first one, we get nothing, it is 0. From the second inner product, we get this one here. When n is equal to m, it will survive, otherwise it will be 0. Otherwise 0. So that means we will only have am times L, okay, from the second inner product. From the last product, we get nothing again. So this is equal to, well, this implies, sorry, it implies what? AM is equal to, remember we start with f of x and cosine here, this one, all right? We start with this. So this tells you basically AM is equal to 1 over L times f of x comma cosine, what was it? M pi x over L. Here we assume that M is non-zero, but if M is zero, this is still true, because in that case, if M is equal to zero, the only thing will show up the first inner product, second inner product, and third inner product will be zero in that case. So we will get the same thing. Okay, so this is true for all M integer. Okay, or maybe natural number, let's say, because it starts with zero. Let's write like 0, 1, 2, like this. Okay. So we get this formula for the coefficient, and this we will use it later. Any question so far with this?
Yes, I wanted to ask. I wanted to ask why we have AM but not the AN.
It doesn't
AM ties
make any. It doesn't make any difference. You say AM, AN, AS. It's just the index, right? You here, since we start with here with M, we get the coefficient AM. Okay, we could start with AM, but that will make some confusions because in the series we also use N. Okay, so that will not be easy to work with. That's why we start with M. But at the end, M is any number, so it doesn't make any difference whether you use M, N, or other things. Okay, it's the name of the index.
Yeah, I got it, Hocam. Also, I wanted to ask why at the end we write 1 divided by L times fx. I didn't get where this part come from.
The last one in the box.
Yes, 1 divided by L times f
Oh,
x.
because remember we start with this f of x comma cosine something, right? And we end up with that one. So it's equal to f of x comma cosine m pi x over L, right? And this implies that AM is equal to 1 over. So divide by L both sides. So we get this from here. Okay, clear?
Thanks. Yes.
Okay. Yeah. Well, you need to think about it a little bit for this computations here. As I said, they will follow from 1, 2, or 3. You may miss some parts here. It's quite reasonable. Okay, but you can easily go over this and check the calculations. Okay, so it's not difficult. Okay. All right.
Hocam ben de bir soru sorabilir miyim?
Hı.
Burada ilk inner product'ı hani m eşittir 0 değilse bu sonuç 0 olur dedik ya. A 0 bölü
Evet.
2 kısım. Orayı bir tekrar şey yapabilir misin? Biraz karıştı gibi olsa.
Tamam, şöyle düşünelim. Şu var değil mi elimizde? A0 over 2 and the other one is cosine m pi x over L, right? This one. Well, we can think of this like A0 over 2 and 1 cosine m pi x over L, right? Same. Okay, but 1 here, you can write 1 here as cosine 0 pi x over L, because cosine 0 is 1, right? Now let's return to number 2 here. Number 2. It says if m is different from n, the result will be 0, right? And in our case, right, so this is n, and m, if m is different from 0, which is n, then this will be 0, okay?
Anladım hocam, teşekkür
Olur
ederim.
mu?
Bir de evet
Tamam.
oldu. Bir de eşitliğin sağ tarafında am çarpı l bulduk ya. Eli
Evet.
şimdi nereden olduğunu anladım. O da cos
Evet.
yine 2'den geldi. Ama o
Aha.
bir tanesinin başında zaten indeks vardı.
Evet.
Tamam,
Şimdi
çarpı.
burada n m'ye eşitken sadece bir sayı gelecek, gerisinde 0 gelecek. Dolayısıyla n m'ye eşitken de am olacak o, tamam.
Tamamdır hocam, teşekkür ederim.
All right. We're done with this. Well, we can also find, remember here, the Fourier series. Where is it? Here, the Fourier series is given by this formula. And in this formula, we find here an. What about bn? Okay. We also find a0. A0 is when n is equal to 0. We have a0. Okay. This formula holds even for m is equal to 0. I didn't check this, but this is true even for m is equal to 0. Okay. You can check this yourself. Now let's find out the other coefficient of sine function bn. I will not do the same calculations, but it's quite similar. So I will just write the formula here. So similarly, let's raise this. So similarly, bn or bm, let's say, n or m, it doesn't make any difference, but let's be consistent. bm is equal to, now instead of cosine, you will take the inner product with sine of something, like in the previous one. You will get 1 over L integral minus L to L. Remember, L is the period. 2L is the period of the function. Okay, f of x sine m pi x over L dx. It's quite similar with am. Now m starts with 1. In the formula, we don't have b0. We don't have b0, right? Remember, in the Fourier series, where is it here? B starts with 1, okay? Bn starts with 1. Here we have a0, but we don't have b0. So this is true for all m. 1, 2, and so, okay? So this, we have another important formula for the coefficients of sine function. All right, maybe let's stop here. So next time we will do some examples with Fourier series. We will write the explicit Fourier expansion of a periodic function with some examples. Question, comment?
Hocam burada am'i de yazarken 1 bölü l eksi l'den l'e integral, yani fx cos mp x bölü l dx olacak.
Evet.
Inner
Onu,
product'ı.
Doğru. Evet, onu öyle yazmadık. Yazsak güzel olurdu aslında. Ama
İki
siz
şekli de
anladınız.
iki şekli de görmek böyle alt alta daha da şey oldu.
Evet. Yani şu aslında 1 bölü L ve bu daha işimize yarar bir formül. F of x cosine m pi x over L dx. Evet. Güzel. Peki.
Aslında burada hocam son bir şey daha söyleyeyim gitmeden. Yani inner product özelliğini kullanarak AM'i ve BM'i bulabildik. Fx cinsinden tabii.
Evet, güzel, bravo. Yani sonunda inner product'la ilgili aslında bir şey kalmadı elimizde, değil mi?
Evet,
Yani
evet.
coefficient'ları integral kullanıp bulduk. Inner product'ı aracı olarak kullandık. İşimiz bitti onunla artık. A'ni ve B'ni F ile kosinüsün F'lesini inner product olarak yazdık. Dikkat ederseniz burada AN neyin koefficient'ıydı? Hani bu formül aklınızda kalması için şöyle düşünebilirsiniz. Kosinüsün koefficient'ı. O zaman aynı hesaplarken de kosinüsü kullanıyoruz. Yine Bn'de sinüsün koefficient'ı. Bn'i hesaplarken de sinüs kullanıyoruz. Yani oradan aklınızda kalabilir.
Tamam. Tamam hocam, teşekkür ederim.
Peki. Any other question? Comment? All right, let's stop here. I will see you on Friday. Bye.
İyi günler hocam.
İyi günler.